This topic will look at how proof by induction works with matrices. So a reminder of the steps for proof by induction. The first step is to assume that the statement is true for a value of n equals k. You would write down the thing that you have assumed. The next step is to show that if this assumption is true, it will also be true for the next number along n equals k plus 1. You'll find it easier if you start by writing the thing you're aiming for before you start. You then start off the inductive process by substituting in the first term, which is usually either 0 or 1. And finally, a conclusion, as the statement is true for n equals 1, and if true for n equals k, will also be true for n equals k plus 1. We've proved by induction it is true for all integer n values greater than or equal to 1. So when proving by induction with matrices, we can use the result that a matrix to a power, so matrix A to the power k plus 1, can be written as A to the power k multiplied by an extra copy of matrix A. So A to the k times A becomes A to the k plus 1. A to the k will usually be part of the result that we have assumed in our first step. So we will multiply by A, and then this will be the thing that we are aiming for in our k plus 1 step. So we're going to prove by induction this result, that the matrix 1, 0, 5, 1 to the power n is 1, 0, 5n, 1. So we're going to start by writing down the thing that we are assuming to be true, that is true for n equals k. So 1, 0, 5, 1 to the power k is 1, 0, 5k, 1. We're next going to show that the result n equals k plus 1 will be true from this assumption. So the thing that we are aiming to get is that 1, 0, 5, 1 to the power k plus 1 will be 1, 0, 5 times k plus 1, 1. So this is just the result up here, but with k plus 1 substituted for n. So we're going to start with 1, 0, 5, 1 to the power k plus 1. Now usually we'd need to worry about commutativity, about whether the matrix, the single matrix on its own came before or after the matrix of the k. However, we don't need to worry about commutativity in this case because it's the same matrix being multiplied by itself over and over. So we can actually put it on either side. So 1, 0, 5, 1 multiplied by 1, 0, 5, 1 to the power k multiplies out to give us the matrix that we were aiming for. So we can say as required. You can double check this. If you'd multiplied this the other way around, because this is just repeated multiplications of the same matrix, you would have still ended up with the same result in this case if you'd done 1, 0, 5, 1 to the k and then multiplied by 1, 0, 5, 1. We now need to show the result is true for n equals 1. So for n equals 1, the left-hand side will just be 1, 0, 5, 1. And the right-hand side will also be 1, 0, 5, 1. Therefore, we can conclude it must be true when n equals 1. And we can finish the proof with our last statement that as the result is true for n equals 1, and if it is true for n equals k, it will also be true for n equals k plus 1. Remember to use the word if here. We have proved by induction that this result is true for all n values, integer n greater than or equal to 1. Next, we're going to use induction to prove this result here. You may want to pause the slide and try this yourself first. So the first line is that we're going to assume that the result is true for n equals k. So this is the assumption we are making, substituting k into the original rule. We're going to then show that this is true for n equals k plus 1. So we're trying to show this. I've substituted in k plus 1 for all of the n's, simplified it down to show this matrix here. So this is what we are aiming to get. Remember, we've not proven this yet. We're just aiming to get 3 plus 2k minus 4 minus 4k, k plus 1 minus 2k minus 1. So we're going to start with the matrix here. 3 minus 4, 1 minus 1 to the power k plus 1. We're going to split this up into the matrix to the power k multiplied by the matrix itself. We can then expand this. We're going to substitute in our assumption. We already assumed that this matrix to the power k could be written as 1 plus 2k minus 4k, k, 1 minus 2k. So we put this in here, expand it out, careful with the matrix multiplication here. Simplifying this down gives us this matrix, which is the one that we said we were aiming for in the first step. So we can put as required at the end to show that it's also true for k plus 1. Finally, we're going to check that it works for n equals 1 by substituting this in. The left-hand side and the right-hand side both become 3 minus 4, 1 minus 1. Our conclusion then, the same sentence as usual. The result is true for n equals 1, and if true for n equals k, is also true for n equals k plus 1. Therefore, it's proven by induction for all integer values n greater than or equal to 1. Now complete exercise 12b on page 260.